So you had some data, you fit some models. How can you tell if your model is good? Well, I've got a short answer. Look at the R squared. Bigger R squared must mean better fit. Like, look at how good this fit is. And it's got a larger R squared. Video over. No. If it was just as simple as looking at the R squared, we wouldn't need to have, part of a lesson on it. So, I don't know if you know what R squared actually tells you. I will tell you later on in the same class. But just looking at the R squared doesn't tell you if your model's appropriate. And actually just looking at the visual fit of your curve to the data doesn't tell you if the model's appropriate. So the point of this next segment of the lesson is, how can you determine if your model's appropriate? All right, so here's some secret data. Well, the data isn't secret, but what it's about is secret. So we've just, we've taken some measurements. We've got an x-axis, we've got a y-axis. I'll reveal what it's about soon. Just right now in your group, pause the video. Decide, just purely on a visual basis, which function is the best fit for this particular data. Okay, so I think if we're just asking which curve hits the points the closest, the answer is D. D is a 6th degree polynomial. A is a linear function, B is a quadratic function, C is an exponential function. But fitting the 6th degree polynomial to your data is not necessarily the best choice for your model. So let me tell you what the model was really about now. The model was actually about the time needed to fold an origami model depending on the number of folding steps. But the data isn't actually about the total elapsed time it takes to fold the model. It's about how long each individual folding step takes. So here you see 5 seconds for the first folding step, 6.7 seconds for the second folding step, meaning that so far we've taken 5 plus 6.7. So far we've taken 11.7 seconds up to step 2. Step 3 is like a really short folding step. Step 4 is a little bit longer, and so on. And so these original data points that you just tried to fit a curve to, that's where this data comes from. It's how long did each individual folding step take. And I think this was real data that our colleague Ehyung McComb recorded when she was folding an origami model. Okay, so before we proceed to our original question, pause the video for a second. What kinds of things do you think would explain why the time in general is increasing? Okay, since I'm not there in person, let me share with you a couple of ideas that I had. One idea might just be general fatigue. I might slow down over time because I'm getting tired of folding. I'm not sure that's the best explanation. That may play some role. I think another explanation might be the more folds I've done before my current fold, the more complex a model I'm holding in my hand. So it might take me longer to figure out what the right fold to make is if I've already made a lot of folds. I don't know if you do origami models, but I think sometimes, I don't really, but I suspect that sometimes you might have to unfold a couple of things in order to do the fold and then refold them. So I think that could be one explanation for why larger fold numbers take more time individually. So now let's ask a slightly different question. We don't just want to ask which model fits the data I've collected the best. Maybe the purpose of collecting the data was to establish a trend that we could then extrapolate. Extrapolate means extend beyond the data that we've recorded. So we just recorded data up to our 8th fold, but what if we want to use this the model that we fit to our data to predict the time it would take for the 10th fold or the 12th fold or the 16th fold if it was a very complex model that we were folding. So same question, pause the video with your group. Which model do you think would be the best model to choose now? So hopefully you chose a model that was different than this one, and we'll come back to which model we think might be best in a second. But real quick, share with each other, if you didn't already, why might this one not be the best choice? So this model, a sixth degree equation, has a lot of freedom to fit points that we have. Like, remember, we had that discussion before about a linear equation is determined by 2 points, and a quadratic equation is determined by 3 points. So it has like a little bit of variation, and a cubic equation is determined by 4 points. So if you have a sixth degree equation, that's a lot of degrees of freedom that you can use to have it change direction and to adjust its curvature to really fit a handful of data values that you have. But now that we've fit the sixth degree curve, if we look at what it's predicting, there's quite a steep slope here. So if we go all the way out to 16, it's going to predict a hugely long amount of time for my 16th fold. But that's probably not very realistic. And the reason that it happened is because we tried to make our fit to the data that we had too precise. In modeling and in machine learning, like in artificial intelligence, this is called overfitting the data. So, the data that we have is just a handful of examples of the thing that we're really interested in, which is future data that we haven't collected yet. So you don't want to actually fit your curve too closely to the data you have if you don't actually have a lot of data. Because it might mean that you're paying too close attention to what's actually just random fluctuation in the data that you've collected. Okay, so what would be a good model to choose? I think probably maybe linear, maybe quadratic. Take a second and say, why not exponential? Okay, hopefully you said exponential growth grows incredibly quickly. It's got the same problem as this sixth degree polynomial. And when we're this closely zoomed in, I don't know if the problem's so obvious, but an exponential function, you are multiplying your y value growth by every fixed increase in x value. So this is going to get extremely large extremely quickly. Okay, so slightly different question. Now we're not necessarily thinking about extrapolating our predictions beyond the data we've collected. Now we're going to think about, what about the next time I fold the same object? Which of these models is going to predict the fold times the next time I fold the same object? Or maybe if I hand it to a different person and the other person is going to fold the same object. So very similar, the next time I fold the same object, I'm not trying to extrapolate beyond the data I've collected. I still want to predict how long is it going to take my fourth fold, or how long is it going to take me to do my sixth fold. So I'm still predicting in the domain of the data that I've collected. But again, you wouldn't want to choose the sixth degree polynomial because we've overfit the particular observations that we made only once. So this isn't going to be a good choice for making future predictions over the same interval. Exponential, maybe. Linear, probably not. I would say probably quadratic. Or it could be exponential as long as we're sure that we're not going to extrapolate past the data that we have. So I guess the overriding point here is you just have to think about the meaning of your data and think about model features such as growth and what those mean in the context that you're measuring. So real quick, say out loud in a sentence, the growth of this linear equation is 2.4. In a nice tight sentence, what does that 2.4 actually mean? This is a good sentence starter. Pause the video. So you could say a sentence like, for every additional folding step, because that's the x-axis, so for every additional folding step, the time it takes to fold that particular fold increases by 2.4 seconds. So now think carefully about this exponential curve. The 1.5 is telling us the growth. What does that growth mean in context? Here it wouldn't be appropriate to say something like, for every additional folding step, the time increases by 1.5, because it's not really increasing by 1.5, or rather that's an ambiguous phrase that doesn't actually mean anything precise. What the 1.5 is really telling you is that the nth folding step is 1.5 times as large as the prior step. That's actually not quite true either because of our shift factor here. But it's telling you that there's a multiplying effect. So you could say approximately, the approximation being, again, because of this vertical shift. So each folding step is approximately 1.5 times the size of the previous one. And when I say size, I mean length of time. It's going to take approximately 1.5 times the number of seconds of the previous folding step. Okay, so in this case, if we want to know which growth model is more realistic between linear and exponential, again, almost certainly linear if it's between these two. So now that we know that you can't just look at numbers, you actually have to think about what makes sense in context, go back to your original context of the paper tube and decide for your particular paper tube model, or rather for the paper tube context, which of the various models makes most sense. And if you're not sure which makes most sense, at least try and eliminate some of the options.